Hey guys, what's up? So today I want to talk to you about linear approximations near x equals 0, okay? So now this is a very important topic in math because in math we like to keep things simple. And well, one way in which we can do that when using linear approximations is to let x be equal to 0, okay? Or to let our base point be equal to 0, okay? So now I'm gonna show you what it means to have a linear approximation near x equals 0, and then we're gonna do some examples, okay? So let's begin. Now we know that the typical linear approximation formula goes the function f of x is approximately equal to the function evaluated at our base point x naught plus f prime times the change in x, which is going to be x minus x naught. Now, what if we said that we want x naught to be 0, okay? So remember, x naught in our x-axis is going to be like a point that is fixed, and we can only choose x values that are close to x naught. So what if we say that x naught equals 0? Well, then we would have the following. We would get that f of x is going to be approximately the function evaluated at 0 plus the derivative at 0 times x, okay? This is the form that we get. And now, if you didn't really get the notion of a linear approximation before, or you don't know why it's called that, well, see it like this. This is going to be the typical y equals b plus m. M is going to be the slope or the derivative times x, okay? This is the typical linear, the linear form of any function. And you can see that, well, this linear approximation has a very evident linear form, okay? So now, once we have this form, we can approximate any function that we want near 0 using this, okay? Which is very simple. So now let's do that for sine x. So we know that sine x would be, so sine evaluated at 0, we know that it's going to be 0, plus the derivative of sine, I'm going to write it over here, so sine of x prime, we know it's going to be cosine x, and if we want to evaluate that at x equals 0, then we know that would just be cosine 0, okay? And remember, cosine, it starts at 1 when it's in the origin, so this would just simply be 1, okay? So we have 1 times x, that is just going to be x, okay? And so we say that the linear approximation for, it's better like this. So sine x is going to be approximately equal to x for values near x equals 0, okay? So now this is a very important linear approximation because it's what we call the small angle approximation. You may have seen some memes about engineers abusing this approximation, taking, I don't know, sine 30 degrees equals 30, which is very wild, and it totally abuses units because 30 degrees, that's a degree, the degree is a unit, but if you get sine of 30 degrees equals 30, 30 watts. It's very weird, and there are many memes about this approximation. But just understand that it only works for values near x equals 0, okay? And well, the memes, they come from when people use x values that are very far away from 0, okay? So yeah. So now let's go with a different function, a function different from sine x. So let's do cosine x. So we know that cosine x is going to be approximately the same as, so cosine evaluated at 0, we know that would be 1, plus the derivative of cosine x, we know that would be, let me do that, so this C looks so weird, so cosine x, the derivative of that would be minus sine x. If we evaluate that at x equals 0, then we know this is just going to be negative 1, okay? Because, this would be actually 0, not negative 1. This is going to be 0, okay? Sine of x equals, sine of 0 equals 0 times negative 1, that's just going to be 0. So now we have that cosine x is approximately 1 plus, this is going to be the derivative, and we know we got 0. So we have 0 times x, this is just going to be 1, okay? So we get this derivative. Now, well, not this derivative, I'm sorry, I was thinking about the slope of the cosine function close to x0, and we get this linear approximation for values near x equals 0, so let me write that, near x equals 0, okay? Now this is another common linear approximation, and actually something that I want to explain now is two very common limits. So two very common limits using these approximations. So I'm gonna do that over here. There's a pretty cool limit that goes the limit as x approaches 0 for sine x over x is gonna be equal to 1, okay? And now I think you can see why that is the case. Well, we're saying that for values that are close to x equals 0, which is perfect, or it's the perfect idea for the limit as x approaches 0, x is going to be a very small number, and we want to have small numbers. So sine x would be almost the same as x, okay? And remember, if you have something that is equal, if you have two things that are equal dividing each other, that is going to be 1, okay? So that is one of the reasons why we say these two guys, they're going to be 1, because this is basically saying that you have sine x over sine x, or the same as x over x, okay? That is basically like the essence of using this linear approximation for that limit. You basically have two things that are equal dividing each other, because, well, the function, as x is very small, which is what the limit indicates, well, these two guys, they're the same, and if they're the same, you divide them, you get 1, okay? That is one of the ways in which you can prove that limit. And now, I think there was a limit with cosine, and yeah, there was one. That basically goes, let me think, it was the limit as x approaches 0 for, it was cosine x minus 1 over x, I think. Yeah, it was this. So, wait, was it this? Yeah, I think it was this limit because there is something, these two limits, they're very important because they appear when you're taking the derivative of sine and cosine using the derivative definition. And this is one of the forms that you get when you're doing the derivative. So now, if you have this, well, something that you can see is the following. You know that for values that are very close to 0, which is what's happening with the limit, cosine x is going to be approximately equal to 1. So this would be the same as 1 minus 1 over x, okay? And it's pretty easy to see that this would be equal to 0, okay? Which is what this limit should give you when you're computing the derivative of, I think it's the derivative of cosine or the derivative of sine, okay? When you're taking those two derivatives, you're gonna get to this limit. And it's very important to know why this limit equals 0, okay? That is something that usually teachers, they just tell you, and we know this limit equals 0. Well, now you have a reason to show that this limit is indeed 0, okay? You basically get cosine x is basically the same as 1 for x values close to 0. So you have 1 minus 1 over 1 minus 1 divided by something that is not 0, but that is very small. Okay, when we take the limit, we assume that x is not equal to 0. So we can say that this has a definite value, and that's 0, okay? So now I think this is the entire video. So we basically went over, to wrap everything up, we went over what a linear approximation looks like near x equals 0. We gave some examples, and I showed you how you can use linear approximations to do very helpful things in math, such as proving these two limits, okay, which are very important when computing derivatives. So yep, that has been everything. I hope that you enjoyed this video, you learned something, and see you in the following one. Don't forget to subscribe, and yeah, that's everything. Bye.